Okay, electrolysis is the use of electrical energy to cause non-spontaneous redox reactions to occur. This is the idea of running a battery backwards, and this takes place in electrolytic cells. It's commonly used to decompose molten compounds into their original component ions. So if we look at this example right here, we have liquid sodium chloride being broken down into solid sodium metal and chlorine gas. And if we assign oxidation numbers down here, like we see right here, we can write two half reactions. So we see that sodium starts out as Na+1, like we see right here. It's going to gain ultimately 2 electrons because we have this coefficient of 2 in front, and it's going to become solid sodium with an oxidation number of 0, just like we see up in our balanced equation up above. So something that is typically oxidized is now being reduced. At the same time, we have the chloride ion right here, because this is Cl-1, losing electrons and becoming Cl2, a diatomic 0, and losing a total of 2 electrons right here, because obviously we started out with 2 chloride ions. So something that is normally reduced is now being oxidized, and here with the sodium, something that is normally oxidized is now being reduced. So you have to be able to look at these half reactions and figure out, is it going what we consider what would happen in a voltaic cell, or something like electrolysis and doing non-spontaneous reactions. Components of an electrolytic cell. You're going to need 2 electrodes and a molten salt or solution, a battery or some other source of electrical current, so we need an outside power source. This outside power source is going to act as an electron pump, pushing electrons into one electrode and pulling them from the other. Oxidation will still occur at the anode, reduction will still occur at the cathode. What we're going to see here is that electrons are pumped into the cathode from the negative terminal to reduce the ions. The electrons are removed during the oxidation process at the anode and travel to the positive terminal, completing the circuit. So we're still going to have electrons moving from the anode to the cathode, but it's basically electrons pulled from the anode and pushed to the cathode from this outside power source. Now let's talk about the uses of electrolysis, one being the idea of electroplating. Electroplating uses electrolysis to deposit a thin layer of one metal on another metal in order to improve beauty or resistance to corrosion. The anode is a piece of the plating metal, so something like gold or silver or copper. The cathode is the object to be plated, so something like a key, maybe a piece of silverware like a spoon, or jewelry. So you should know that electroplating is just a type of, a way to use electrolysis in everyday life. Now we're going to talk about the stoichiometry of electrolytic processes. It's going to show how many electrons are needed to achieve an electrolytic process. For any half reaction, the amount of substance that is reduced or oxidized in an electrolytic cell is directly proportional to the number of electrons passed into the cell. The number of coulombs passing through a cell can be obtained by multiplying the amperage and the elapsed time in seconds. In order to see this, it's going to require a number of steps. So we need to follow these steps in order to figure out our end problem here. So one of the things that we should realize is that coulombs is equal to amperes times seconds. So step 1 is to convert the current and the time to a quantity of charge in coulombs. So amps times time is equal to the total charge transferred in coulombs. Step 2 is to convert the quantity of charge in coulombs to moles of electrons. Step 3 is to convert moles of electrons to moles of substance. And finally, step 4 is to convert moles of substance to grams of substance. So let's look at an example. Calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten AlCl3 if the electrical current is 10 amps. So we're going to start out by calculating the coulombs of electrical charge that are passed into the electrical cell. So the way that we're going to do this is we're going to take our 10 amps, multiply it times 1 hour, and we're going to convert that hour into seconds. So we know that 1 hour is equal to 3,600 seconds. So hours times hours. And we know from in the middle of page 9, I had written coulombs equals amperes times seconds. So if we do this, we'll have amperes times seconds. So if we multiply this together, we'll get 3.60 times 10 to the 4th coulombs. The next thing that we're going to do is calculate the number of moles of electrons that pass into the cell. So we have this 3.60 times 10 to the 4th coulombs, and we're going to convert that into moles of electrons. And 1 mole of electrons is equal to 96,485 coulombs. So coulombs cancel coulombs. So if we work this out, we should get 0.373 moles of electrons. So all I've done so far is take an amperage and a time. I've converted that time over into seconds, multiplied amps times seconds, gotten coulombs, and then taken that coulombs using Faraday's constant and converted into moles of electrons. Now what we're going to do is to relate the number of moles of electrons to the number of moles of aluminum being formed using the half reaction for the reduction of aluminum ions. So we have 0.373 moles of electrons, and we're going to get to 1 mole of aluminum. Okay, 1 mole of aluminum. And we know that 3 moles of electrons were transferred based on the half reaction. So if we look at that, we should get, if we work this out, we should get 0.124 moles of aluminum. Then finally, the last thing that we want to do is take that moles of aluminum, which is 0.124 moles of aluminum, and convert it into grams. And we know that the atomic mass of aluminum is 27 grams, and we're going to divide that by 1 mole. So moles cancel moles. So when we do this, we finally end up with 3.36 grams of aluminum. Let's look at one more example. How many grams of copper may be electrodeposited by a flow of 5 amperes for 2 hours through a copper 2 nitrate solution? So if we look at this, we want solid copper. We look at our formula right here, and we know that our Cu plus 2 ion is going to gain 2 electrons and become solid copper. And we need to know those 2 electrons right there is the number of electrons being the moles of electrons being transferred. The first thing that we want to do is take our 5 amps, multiply it by the times. So 2 hours. But we don't want hours, we want seconds. So we know that there's 3,600 seconds per 1 hour. 1 hour. So hours cancels hours, and if we multiply this together, we'll get 36,000 coulombs. So this is always going to be your first step. Taking your amps, making sure that if whatever time you have, that it's converted to seconds, if it's not already in seconds, and getting it to coulombs. That's always going to be your first step. After that, you can do it by step and one-step reactions, or you can do it like I'm going to do it right now as one huge just dimensional analysis problem. So I'm going to start out with my 36,000 coulombs, and I'm going to convert that into moles of electrons. And I know that in 1 mole of electrons, 1 mole of electron, so mole of electrons, I have 96,485 coulombs. So coulombs cancel coulombs. Now what I want to do is I want to look at the ratio between how many moles of electrons were transferred for every 1 mole of copper. So in 1 mole of Cu, which I have up here, I know that 2 moles of electrons were transferred. So moles of electrons cancels moles of electrons. Now I'm in moles of copper. Ultimately, we want grams of copper, so I know that in 1 mole of Cu, I have 63.5 grams of copper. So again, moles copper cancel moles of copper. I'm left with grams. So now all I need to do here is multiply my 36,000 times 1 times 63.5 and divide that by 96,485 times 2, and my final answer here should be 11.8 grams of copper. This is really important for you to know how to set up and go through this step by step, especially through the remaining part of your homework.